Hello, hello, and welcome back to CS 500 Design and Analysis of Algorithms, also known as Advanced Algorithms. In this course, we focus on the analysis part and then design algorithms subject to the analysis we want to consider. So if we want to design efficient algorithms, runtime efficient algorithms, then of course we focus on running time. We want to analyze algorithms with respect to their memory use. Then we design the algorithms entirely differently. And if we want to analyze algorithms in their worst case behavior, that's a classical way. Or if we want to analyze algorithms with respect to their average case behavior, or the amortized case behavior, or the expected case behavior, that can make a huge difference in how to approach the design of such algorithms. So that being said, today we're going to start talking about chapter 2. Chapter 2 is about tree data structures, because tree data structures will serve as a prime and very important example of amortized cost analysis. So maybe you have seen the data structures we consider here in previous courses, such as CS300, Introduction to Algorithms, or in data structures course. But please bear with me, because the perspective we take here is the perspective of analysis. And this is kind of a preparation for the new data structures that we will then use to illustrate the amortized case analysis. So let me start by sharing the slide. Here we are. Right, you can see the slide. Okay, so the content of this chapter is that we first talk about, recall about what is a data type after all. And actually there's a close correspondence between data types in computer science and structures in mathematics, more precisely in logic, and even more precisely in model theory. And we emphasize the difference between hardware and mathematical data types, where the purpose of object-oriented programming is to hide details of the implementation to make data types appear as mathematical data types, and to hide the underlying hardware according to our general approach of abstraction. Then we will briefly recall basic data structures and derived data structures, with a focus on linked data structures, because that will lead us to tree data structures. We'll recall AVL trees, their definition, and their properties, quantitative properties, which will be the key to our analysis of algorithms that use AVL trees and algorithms that implement AVL trees. These are the two sides of the coin, that we design data structures and we realize data structures with algorithms. But on the other hand, then we can build on these data structures and data types for more advanced algorithms, kind of climbing up the abstraction hierarchy. So based on the analysis, then we will discuss operations on AVL trees, insert and delete and searching, and maintaining the AVL property. We'll analyze them with a classical cost, still the worst case running time here, and then we'll be led to the deficiency of AVL trees. Something that AVL trees cannot do well is the merge operation, which will lead us to consider even more complicated data structures, more complicated data structures, namely binomial trees and collection of binomial trees, so-called binomial heaps or binomial forests. We will recall how binomial trees and binomial heaps are defined. We will recall operations on such binomial trees and heaps, and we will analyze them with respect to their cost, first in the worst case setting, but then also in the amortized setting. And the operations we will consider are the extract min operation and the decrease key operation and the merge operation. So that's our plan for chapter 2 of design analysis of algorithms. That being said, let's move on to the first part, hardware data types versus mathematical data types. And you might recall the computer game called Civilization. In Civilization, the goal is to rule one country of your choice, the player's choice, and the other countries are ruled and governed by the computer. So it's a game playing one player against the computer. At least in the early ages, it was one player against the computer. Maybe nowadays it's possible to play several real players simultaneously over internet. But how did the computer in this game is, I think, from the 1980s. So how did the computer players rule countries? They were governed by a kind of rudimentary artificial intelligence, and different leaders of different countries were described by some numerical parameters that governed their general approach. For example, India would be governed by a virtual Gandhi, and reflecting the actual Gandhi, this Gandhi was described among them several parameters with an aggression parameter, which was very low, namely aggression level 1, whereas other countries and leaders would be governed by maybe more aggressive virtual entities. And one of the rules in this game was then that during the course of such a simulation, when a country would develop democracy, then its aggression level would further decrease. So democratic countries are less likely to join war. And so this was the rule: whenever a country adopts democracy, decrease its leaders' aggression parameter by 2. Now, what happens if you decrease 1 by 2? What happens when India develops during its simulation of its history, develops democracy? Well, mathematically, decreasing 1 by 2 results in -1. That's mathematical integers. But the computer game Civilization was implemented using hardware integers, not mathematical integers. And in hardware integers, if you decrease 1 by 2, there's a wraparound. So if the hardware integer is a byte, then the wraparound value is 255. And this is exactly what happened, that when India, during the course of this simulation, developed democracy, it suddenly became extremely aggressive and started to wage war against its neighbor countries, which was kind of a gag, or you could say it a programming error, which was not maybe the intended behavior of the original programmers. But the course of this discrepancy is, of course, the difference between hardware integers and mathematical integers. Hardware integers having this wraparound effect, mathematical integers not having the wraparound effect. So that's why it's important to distinguish hardware data types from mathematical data types. And well, we usually are kind of educated with mathematical data types and didn't expect this discrepancy. And in many cases, the discrepancy can be neglected. But as this example points out, it may result into simple programming errors. Another example that you may be aware of is, of course, arrays, right? So popular source of computer exploits nowadays in internet, such as like Heartbleed, is when one accesses arrays beyond their range of definition, their allocation, then computers might start to access undefined memory or memory occupying with other data, and this can be harnessed. So that's again an example of a difference between hardware data types, the way that arrays are implemented in hardware on the one hand, and on the other hand, finite sequences that would be the mathematical counterpart to hardware arrays. And accessing a finite sequence beyond its specification, its definition, is of course mathematically undefined, and computers may or may not detect that depending on the hardware details. So long story short, be aware of the difference between hardware and mathematical data types. Right? Now let's moving on to abstract data types. Abstract data types, again, occur in both computer science and mathematics. And the goal is to really be able to ignore, in the sense of information hiding, details about how these data types are implemented, as one would say in computer science, or how they are defined or constructed, one would say, in mathematics. Let me start with a simple example of that we already just discussed, namely integers, right? So on the one hand, there's a hardware, byte and word both exhibit wraparound effects. Bytes have them earlier, words have them later, whereas mathematical integers don't. And abstraction means we ignore how this data type of integers is actually constructed or implemented, and we only make use of its properties with or without wraparound. So for example, an integer in hardware is of course realized maybe by a finite sequence of bits, but this number of bits could be constant or could be dynamically adjusted. If the integer value becomes larger, then the software might allocate more additional bytes or words, such as to hide and prevent wraparounds from occurring. Also, yeah, it could be running on a 8-bit CPU, 16-bit, 32, 64-bit. All this is hidden by modern programming languages. And also in mathematics, how do we construct integers? Right? There's the axiomatic approach that only specifies the properties, but then in the foundations of mathematics, we better make sure that such a data type, mathematical data type with these properties even exists, right? And yeah, so for example, John von Neumann was famous, among many other things, for constructing integers, building on set theory as foundation. So that's the so-called von Neumann integers. Then there are the Peano integers, which are axiomatic integers, and there's other ways of how to construct integers mathematically. Now that's a simple data type, and let me remind you of the operations that this data type supports. There are two constant operations, 0 and 1, and then there are binary operations like addition, multiplication. There's unary operations like negation, and then there's a division operation. which is division with remainder, usually in integers. And then there's a predicate, namely the comparison predicate. The predicate is different from the other operations in that it does not, it takes an integer, that's true for all the operations, but the predicate returns a Boolean value, true or false, whereas the other operations return another integer. And that's, how to say, yeah, two perspectives, both in mathematics, we know these operations and the predicate, and in computer science, we have these operations and the predicate usually provided on the integer data type. Now let's move on to a more involved example, namely the real numbers. And with real numbers, again, we need to be careful and observe that there's often, or even usually, a discrepancy between the mathematical data type of real numbers and the computer scientific hardware data type of real numbers. Namely, this is not real numbers, it's floating point numbers usually. So, for example, single precision, double precision, extended precision, there are various floating point data types usually provided in software or in hardware or in a combination of software and hardware. But as we had with integers, there's a discrepancy between the hardware data types, computer data types, and the mathematical data types. And let me use this opportunity for some kind of cross promotion, because my own research is actually about bridging this gap, about creating computer data types that agree with the mathematical data type of real numbers. Similar to modern programming languages providing integer data types that agree with the mathematical data type of integers, for example, big int, or in MPFR, long integer, using software to simulate mathematical integers. And the same is actually possible. People in general don't believe that, but it is possible to really simulate mathematical real numbers on a computer by using a variable number, for example, of double precision floating point numbers or high precision floating point numbers, such that to the user they appear as equal or rather indistinguishable from mathematical real numbers. Right. So whenever the precision turns out to be insufficient, then silently increase the precision so that the user program behaves as if it were running on exact mathematical real numbers. So again, currently the prevalent approach also in numerics is differs for real numbers from hardware data type, but it is possible, and that's kind of my research, to make it equal to. And okay, enough advertisement for my research. Let's now move on and again also recall what operations are supported by real numbers mathematically and by floating point numbers computationally. Again, we have constants, among others, 0 and 1. We have arithmetic operations. We have a comparison predicate, and this is actually where the differences start to become even more subtle, because you may recall from numerics 101, don't test for equality or inequality, whereas mathematically, of course, tests for inequality are essential in proofs or in constructions like Gaussian elimination. But that's an entirely different story. So long story short, on computer science side, how do we implement real number data type, for example, using double precision, which is not an exact implementation. And mathematically, what are real numbers mathematically? And again, there are various approaches mathematically. First, there's an axiomatic approach, There's famous logicians have proposed different axiomatizations of real numbers. For example, Tarski, Alfred Tarski has provided such an axiomatization. And then there are constructions to construct real numbers. And the purpose of this construction is to make sure that structure with these axioms really exists. And after having constructed, I think every student in mathematics should be presented at least once with one possible way of constructing real numbers, and then we can forget again how it's constructed. Same way we can forget how computer circuits are implemented in using quantum mechanics, and then abstract from that part and simply build on that. And two popular ways of constructing real numbers are, one approach is using Dedekind cuts, and another way is using equivalence classes of rational Cauchy sequence. And at the end, what they both approaches construct are then proven to be actually isomorphic structures, and then we can really forget how they have been constructed and simply operate on them using their properties, that is, using their axioms. And the same is true for object-oriented programming, where we hide how the data type is being implemented and only its properties matter. So having thus emphasized the importance of abstraction on the level of data type, we can then move to derived data types, such as stack of integers, stack of real numbers, stack of bits, stack of strings, stack of graphs, or stack of stacks. That's one advantage of having abstract or derived data types. We can simply iterate and create more and more advanced data types from them. And operations supported by a stack data structure are push operation, pop operation, and again a predicate, namely whether the stack is empty, in which case pop is not permitted or not well defined. Another derived data type is queue, similar to stack. We can have a queue of integers, queue of real numbers, queue of bits, strings, graphs, or queue of stacks, or a queue of queues, right? And the operation supported in queue is the enqueue operation, the dequeue operation, and the predicate whether the queue is empty. And the difference between stack and queue is, of course, the axioms, right? So, for example, for a step, we have the property if we push something and then immediately pop, then it will return the original element. Whereas for a queue, if we enqueue something and then dequeue immediately after that, it might usually be a different element. This is reflected by the acronyms stack being first in, last in, first out, whereas a queue is first in, first out, right? Another derived data structure or data type is array, static or dynamic array of an existing data type. So we can have array of integer, array of real, array of stack, array of queue, or array of array, which is simply a two-dimensional array. And operations supported on the array is index access, write access, or read access. And then there's the size operation, which returns the current size of a dynamic array. It's also defined for static arrays, but then it's less important, right? For dynamic arrays, we can have a resize operation. We want to increase or decrease the size. And then there might be a search operation. And I haven't yet started about talking about the algorithmic cost of these operations. So that's about arrays. And now let's talk a little bit about cost. That's again something that is usually axiomatized. being abstract. So, for example, one usually supposes that accessing an array has constant cost. Now, speaking in terms of bit cost and how the arrays are implemented, could be considered unrealistic, right? So maybe it takes at least cost log n to access the nth element, because log n is the binary length of the index, right? So depending on how precisely we want to our analysis to reflect actual hardware implementations, how realistic our estimates we want to be, that affects how we should, what cost we should charge. Remember, we had the similar discussion regarding integer multiplication. A simple approach is to assign one cost 1 for each integer multiplication, but a more realistic one is to charge cost n log n, right? Same here. And searching, on the other hand, is rather expensive on an array unless it's sorted at least linear. But again, one could also say that the cost should be n log n, depending on the binary representation of the access integer. Then we have arrays, sorted arrays. Sorted arrays support searching at more efficient time, logarithmic time. Here the requirement is, of course, that the data we're storing in the sorted array must be equipped with the total order. Otherwise, we cannot even speak about a sorted array, right? Unsorted arrays can have any data, sorted, ordered or not, but the sorted array, the underlying data type must be totally ordered, which is true for integers, for real numbers, but which is not true for stacks and queues, for example. Operations supported by a sorted array or aforementioned sort operations, usually also delete and an insert operation. Searching now is very efficient, logarithmic time using binary search, but insert and delete now becomes very inefficient, whereas inserting and deleting a dynamic array just means appending an element. Then we'll move on to more advanced data structures, such as a priority queue. A priority queue supports find min element and insert an element. And we're going to discuss how to implement these operations efficiently. Namely, the goal is to have them implemented in logarithmic running time. And if we naively implement a priority queue on an array, then it will have linear cost, but using our linked data structure, we will be able to do that in logarithmic time. That leads us to linked data structure. So let's talk about some basic, recall some basic examples from data structures course. Here you see a doubly linked list, right? So where every element is has a pointer to the next element and to the previous element in that linked list, so we can move back and forth. And usually one adds 1 or 2 sentinels, namely a dummy element, which is linked to by the first element, and a dummy element, which is linked to by the last element. And that is more convenient in implementations. And such a doubly linked list now allows to insert and delete elements in constant time, whereas arrays had this linear time because we needed to make room for the new element inside. Therefore, we had to shift up and down all elements. On the other hand, searching a linked data structure takes linear time. In the worst case, we will need to run through the entire linked list, even if the linked list happens to be sorted. So binary search is not supported by a linked data structure in general, and therefore searching takes long time. And this motivates other linked data structures such as binary trees. So here you see an example of a binary tree. A binary tree, every node has at most two children. So here this one has two children, this one has one child, and this one has 0 children. This is called a leaf. And in a binary, in a such a tree, this is actually a binary search tree. Binary search tree have the additional properties that all elements on the left subtree are less or equal, and all elements in the right subtree are strictly greater. Okay. You see that this is also true recursively. All elements in the left are less, and all elements in the right are greater. And these kind of search trees allow for searching, insertion, and deletion in time, which is now proportional to the height. So now we have an important second parameter, namely the height of such a data structure, not just the number of elements in the data structure as here, but also kind of the shape of the data structure, the height. So now we have two parameters to consider, and we want, of course, to be optimal. And what does it mean to be optimal? We see in a binary tree with height h can have up to n equals 2 to the h plus 1 minus 1 elements, so up to exponential. And that means conversely that the height must always be at least logarithmic, and in an optimal binary search tree, that height is asymptotically equal to this optimal. Let me say that again. Height logarithmic in n is necessary, and in a good balanced binary tree, we are away from this optimum by at most a constant factor. So good binary trees have height O of log n. How do we create, and even more importantly, how do we maintain such a good balance? That's an important question, because there also exist far from optimal binary trees. Degenerate trees have height, which is O of n instead of log n. Here you see an example of a degenerate binary tree. Yes, it's a binary tree, right? But it doesn't really make use of the binary property, and therefore it has a very bad height, linear height, which results in very inefficient algorithms. Now let's talk about, this also indicates that in general, it is very costly to maintain balanced trees. So that's where AVL trees come into play. In AVL trees, cannot provide a trade-off between being optimally balanced on the one hand, on the other hand, the algorithmic cost of maintaining that balance. Maintaining optimal balance is costly algorithmically, but operating on a balanced tree is cheap. So that's a kind of two extremes for balanced, fully balanced trees. On the other hand, AVL trees allow for, on the other hand, degenerate trees are easy to maintain, but are costly to operate in, and AVL trees provide for a good trade-off between these two extremes. So let us recall from CS300 or from data structures the definition of an AVL tree. An AVL tree is a binary tree such that any two sibling subtrees have height difference at most 1. So that's a definition of AVL tree, and this is to be understood recursively. So let me show you some examples of AVL trees here. So here you see T0 is an AVL tree with one element, so it's just a degenerate root. T1 is an AVL tree with two elements. T2 is an AVL tree with four elements. T3 is an AVL tree with 8 elements, and so on. So here we see these AVL trees, and yeah, let's verify at the example of T3 that it is indeed an AVL tree. And as I said, we need to verify that on all levels. We need to verify that for the root, that the two sibling subtrees have height difference at most 1, right? That's true. This one is 1, has height 1, by one more than the left one, than the right one. But also recursively, the left subtree here, its sub-subtree has height at 1 more than the right subtree, and so on. And same for T4. And this verifying that recursively corresponds actually to the observation that in this example, these are just example AVL trees, the left subtree of T4 is actually T3, and the right subtree is actually T2. So in this example, at least, we can immediately verify recursively. Once we verified that T2 and T3 satisfy the AVL property, then from that it follows that also T4 satisfy the AVL property. So these are just examples, but they have a particular property. These are so-called extremal AVL trees. They are minimal AVL trees for a given height. So this is an AVL tree of height 0. This is an AVL tree of height 1, or height 2, height 3, height 4. And these are minimal in the sense that these are the smallest AVL trees, this AVL trees with least number of elements, subject to the given height 1, 2, 3, and 4, for example. And this is easy to see. If you remove any node here in T4, then either you violate the AVL property or you decrease the height. So these are the AVL trees of smallest height for a given number of nodes. And this given number of nodes, here, let's call that n of h, the minimum number of nodes of any AVL tree of height h. And here we have this recursive iterative construction of such a minimal number of nodes. And what we're now going to do is we're going to derive a formula, explicit and asymptotic growth of this minimal number of nodes of AVL tree of height h, which will turn out to be crucial in our analysis of AVL tree search, insert, and delete operations. So bear with me when we now analyze this quantity, the minimal number of nodes of an AVL tree of height h. And we observe that kind of the induction start, the minimal number of nodes of an AVL tree of height 0. This is the unique AVL tree of height 0. Plus 1 is actually F2, F3. So let me say it again. The minimal number of nodes of an AVL tree of height 0 is, of course, 1, right? Adding 1 results in 2, and 2 happens to be the third Fibonacci number that, if you recall, Fibonacci numbers are defined by F0 being 0, F1 being 1, and FH plus 1 being FH plus FH minus 1. So in particular, F3 is indeed 2, which gives this equality. And then on the induction step, the minimal number of nodes of an AVL tree of height h plus 1 is the number of nodes of an AVL tree of height h plus 1 plus the number of nodes of a minimal AVL tree of height h minus 1. So what you see here is that we can construct minimal AVL trees recursively, we take one AVL tree, minimal AVL tree of height h. We want to take one minimal AVL tree of height h minus 1, and we glue them together by adding one additional root, as you see here. So this is kind of our inductive analysis of minimal AVL trees. And now we, in order to solve this recurrence, we make a trick, namely we add one on both sides. We add one here and we add one here. And then we see that this is actually the same recurrence as for Fibonacci numbers, right? Only not for Fibonacci number, but for Fibonacci number plus 1, because here we have always a plus 1. So, and we have a different induction start as for Fibonacci numbers, but this means that this is equal to fh plus 4, right? So they satisfy the same inductive recurrence. So putting things together, we arrive at this. And for Fibonacci numbers, we know everything. We have explicit formula, Binet's formula. We have asymptotic growth, exponential asymptotic growth. And thus the same applies to this new quantity, minimal number of nodes of AVL tree of height h. So also this number must grow exponentially, with the base being the golden mean. And then turning things around, solving this means conversely that the height is logarithmic in that number. Let me say that again. The Fibonacci number grows exponentially in the index, and therefore also the minimal number of nodes of an AVL tree of height h grows exponentially in h. And now solving for h, taking the logarithm of both sides, means that h will be logarithmically in this number of nodes up to some constant factor. And this is exactly what we've been looking for, right? This means that the height of AVL trees, of minimal AVL trees, and therefore of every AVL tree, will be at most logarithmic in the number of nodes. And so AVL trees are up to constant factor optimal binary trees. So that's our analysis. And now we take a short break to allow you to digest this and to allow you to ask questions. So welcome back, and thanks for your questions in the chat. No, questions are not mandatory, but some of you have actually raised very good question. So one question I'm happy to delve into is, what operations have complexity O of log fh? So that's a good question, because this is exactly what we're going to talk about on the next slides. For now, what we've done here, let me recall for your benefit. So we have defined what is an AVL tree. We've defined what is a minimal AVL tree of given height, and we have analyzed how many nodes does a minimal AVL tree of given height h have. Then we've seen that a minimal AVL tree of height h has exponentially in h, exponentially many nodes. And then solving conversely, that means that a minimal AVL tree has height at most logarithmic in its number of nodes. And since that holds for minimal AVL trees, it holds for any other AVL tree as well, because larger AVL trees have the same height but more nodes. So any AVL tree has height at most asymptotically logarithmic in the number of nodes. And this is, as you recall, asymptotically optimal. Balanced binary trees have height equal to the logarithm, and AVL tree has height at most up to a constant factor logarithmic in the number of nodes. So there's a constant factor kind of that we're spending, that we're allowing as additional in to relaxing from balanced binary trees to AVL trees. So we allow for constant factor overhead in height compared to perfectly balanced binary trees. But as we'll see, this spending of a constant factor allows for much more efficient maintenance operations on AVL trees, whereas maintaining perfect balance on balanced binary trees is can be excessively costly, can cost up to linear cost O of n, whereas maintaining the AVL property has only logarithmic cost. And you recall that many operations on general trees have cost parallel to the linear in the height. So whenever we search, for example, for an element in an AVL tree, we can do that in time linear in the height and therefore logarithmic in the size. And as we will see, also other operations, insert and delete operations can maintain that property, and that's a big benefit for AVL trees. So let's stop here with the topic of the lecture. Next time we're going to talk about operations on AVL trees, insert and delete operation, and how to restore the AVL property after each of these operations. In the case of balanced binary trees, each operation, insert and delete, can easily destroy the balance properties. Same for AVL tree, but in AVL tree, restoring the AVL property turns out to be relatively cheap. Complicated, to be fair, algorithmically complicated, but with cheap cost, again, logarithmic cost. And this is what we're going to talk about next time. So as usual, I will stay online and answer your additional questions in the chat. But let me stop sharing the slides for now and turn off the video. If you have further questions,